Thank you. On behalf of Tomiko, we are grateful for your attendance this morning. I will be speaking about formulation strategy for latex paints. In particular, formulating paint with multifunctional N-Alkylalkanolamines. Tomiko is a global integrated chemical manufacturing operation that specializes almost exclusively in nitrogen bases and amines. Ergo, the association of this talk almost exclusively with amines. But the greater logic of formulating and optimizing paints for off-diagonal effects is relevant to many other components of paints as well. And now, in outline form, what I'd like to cover today is a sort of an abstract representation of the idea of an off-diagonal effect optimization, and I'll do that with the off-diagonal grid. I'll then present 4 case studies of the methodology and the benefits and the implementation of off-diagonal effect optimization. We'll then talk about some of the other peripheral benefits that can be obtained through the use of multifunctional N-Alkylalkanolamines, and talk about some formulation starting points that are relevant to this type of a study. Now, what I mean by a multifunctional AAA is a pH-adjusting neutralizing alkanolamine that is of somewhat higher molecular weight and structural complexity than what you might normally assume as a commodity, you would use as a commodity neutralizing base. So ammonia or very low molecular weight hydrophilic alkanolamines would not be considered multifunctional alkanolamines. But more structurally elaborate and higher molecular weight alkanolamines would be multifunctional AAAs. So we'll start with this representation of the strategy, which is the off-diagonal grid, the off-diagonal matrix. Paint as sold is a complex formulation. It's a complex multi-component formulation. It contains oftentimes more than 10 separate additives which are used for various reasons. And along the diagonal of this matrix, what you see is the primary reason that a given additive is used in a paint. Pretty much every additive that's formulated into a paint is added for one primary reason. The solvent, water oftentimes, is added as the vehicle, as the carrier for all the other components of the paint. The binder in the resin, obvious function, functions as the binder for the pigment particles, etc. We're all familiar with why the pigment is added, to provide opacity, color, light scattering. The surfactant is added to modify the flow and leveling of the coating, as well as to maintain color stability. Thickeners are added to modify application properties, high and low shear thickeners, etc. And alkanolamines or ammonia or whatever is used in this category of additive would be the pH adjusting agent, and dispersants, and finally biocides, and perhaps a few other additives as well. Now, we're not going to focus today on the diagonal. What we're going to focus is on the off-diagonal effects. And the only ones of relevance that I've noted in this particular slide are the ones in the row for the alkanolamine. But we would certainly recognize that if we choose water as a solvent, for instance, we're going to have a big negative over here in biostability. Solvent-based paints are far less prone to colonization by microbes than water-based paints are. So that's an example of an off-diagonal effect, a negative off-diagonal effect. And what we hope to demonstrate today is that the choice of an appropriate N-Alkylalkanolamine can result in some fairly significant benefits in terms of biostability. We're not going to demonstrate that today, but it is the case in terms of colloid stability, pigment dispersion, emulsion stability, and coalescence in particular. So I'll begin with a very simple study of alkanolamines versus ammonia. Ammonia being the simplest base to represent a non-functional, simple pH adjusting agent. And so we'll compare ammonia to more structurally complex alkanolamines. And what we'll do is we'll take a look at a pretty standard formulation. We have an acrylic resin-based paint, and we have a formula that was optimized initially for the use of ammonia. We're going to do an iso-pH substitution of an amount of a more complex alkanolamine, in this case Advantex, a product that is sold by Tomiko. And we're just going to take an initial look at how this paint performs. So here we've got sort of standard dispersants, and we're using a somewhat non-standard silicone surfactant and defoamers, etc., Kathon type biocide, propylene glycol, antifreeze, etc. first thing we're going to do in this paint is adjust the antifreeze level, because certainly when you switch from ammonia to a more structurally complex alkanolamine, you're very likely going to be able to reduce antifreeze. If we look at the ammonia-based formulation, and which is loaded with about 30 pounds per 100 gallons of propylene glycol antifreeze, 0.3% by weight, we can pass 3 freeze-thaw cycles with about a 12 Ku change in viscosity after going through 3 freeze-thaw cycles. In the case of Advantex, we're going to adopt different levels. We're going to try about 12 pounds, 6 pounds, and 0 pounds of propylene glycol, and exactly the same paint, other than for the substitution of Advantex for ammonia. What we notice is that we can reduce the propylene glycol level all the way down to about 6 pounds per 100 gallons, and still pass 3 freeze-thaw cycles with a minimal change in viscosity when using Advantex. When we try to reduce the propylene glycol level in the ammonia-based paint, we see that immediately upon reducing that level, we fail after the first freeze-thaw cycle. So this is sort of the standard logic of a ladder study and the optimization of a paint formula. You have an existing paint, you're going to try a new additive, and then you're going to go back and look at what other things can be changed, because the use of a new additive has now changed the entirety of the situation. Because now your paint may be over coalesced now. In this case, it was obvious there was obviously too much antifreeze, and so there's a cost savings in taking out 25 pounds of propylene glycol and replacing that with water. But we can go beyond that. Once we've determined the optimal level of propylene glycol in this paint, we can then go on and look at all the other additives, which we did, and I've shown a summary of the reductions that were possible here. We were able to reduce pigment dispersant, surfactant, and defoamer as well. And you can see that upon switching from ammonia to Advantex, we have a 50% reduction in necessary pigment dispersant, a 50% reduction in the necessary surfactant, and a 40% reduction in the defoamer. And there was an 80% reduction in necessary antifreeze, as discussed on the previous slide. So we now have a significantly more economically feasible paint. We have a cheaper paint formula. And when we put all that together and summarize it with just a few basic paint performance numbers, we see that our new paint is just as functional as the old paint. So with all these reductions in pigment dispersant, antifreeze, defoamer, surfactant, etc., we still have a very functional paint. We can pass low temperature film formation tests, and has good leveling, and the viscosity difference after 3 freeze-thaw cycles is only 12 Krebs units by Stromer viscosity. So that's sort of one example of where a functional AAA can take the place of a simpler, more hydrophilic neutralizing base and result in economic benefits. It can result in a cheaper paint formula overall. Now, I'd like to go on and discuss some other things that you can use with multifunctional, some other things you can do with multifunctional AAAs, and maybe go into a little bit more of the science behind it and the reasoning why the replacement of simpler, completely hydrophilic amines with higher molecular weight, more functional amines results in these improvements. So the first thing we'll talk about is pigment dispersion. And we'll look at things like differences in tint strength as a function of the amine and potential grind capacity. I think many career paint formulators are familiar with the fact that multifunctional alkanolamines act as supplementary pigment dispersants. Certainly when you switch from ammonia to any multifunctional amine, you will be able to reduce the level of your pigment dispersants significantly. You'll also have an easier time in the grind because you won't have ammonia evaporating from the grind, and the number of other ergonomic benefits that you'll experience as well. In this particular case, we'll talk about this base paint. This is like an exterior concrete type paint with a styrene acrylic resin, a bunch of standard additives, a little bit more of a European type additive slate here. But again, just dispersants, biocides, etc. Standard sort of a white base paint. And here's our colorant concentrate. Here's a phthalo blue colorant concentrate that we're going to take a look at. If we do 4% colorant in the base white paint, 2 different alkanolamines, a higher molecular weight multifunctional alkanolamine and a multifunctional alkanolamine, but a lower molecular weight, less structurally elaborate alkanolamine, you can see that you have a deeper tint with the more multifunctional alkanolamine. And that's probably just a result of enhanced pigment dispersion, better pigment dispersion. We do rub-ups to make sure that there's no DE, there's no selective flocculation of the white pigment or the colored pigment in this case. And this might be of an economic advantage if you were developing a new color palette, because now you could perhaps develop a deeper blue tint with less color. Color and concentrates are certainly one of the more expensive elements in a consumer paint. So this might be an example of how you would use enhanced pigment dispersion to differentiate or to establish the value of a multifunctional alkanolamine versus ammonia or caustic. And this type of comparison is consistent for a number of pigments, including yellow iron oxide type pigments and carbon black, very high surface area carbon black type coloring concentrates as well. And what we have on this slide is just the formula for the coloring concentrates that we used. Now here's another paint. Here's a semi-gloss white paint based on a it's an old styrene acrylic union carbide resin. It's got a new name now. But we just took sort of just a standard base white out of a reference book and asked ourselves, what would we use as a grind for this paint? So we just pulled this out of the paint and said, this might be something that we try to grind in order to make up this paint. So we just have a simple grind with TiO2, a dispersant. We put all the alkanolamine into the grind in this case, and some defoamer and some antifreeze. Sort of arbitrary selections of what we were going to pull out and put into the grind. And what we look at here is the viscosity of the grind as a function of time and temperature. Now you read this from right to left, where we're going to start the grinding over here, and then after a certain amount of time, I don't remember exactly how long, but a minute or so, we're going to start to read the temperature and the viscosity. And the grind viscosity decreases as you start to grind the pigment concentrate and smooth it out a little bit. And what we see is that what I would characterize as less functional, more almost essentially completely hydrophilic alkanolamines cluster along these lines in terms of temperature and viscosity. And then more multifunctional, higher molecular weight, somewhat more structurally elaborate alkanolamines are clearly in a distinct category on their own. I can repackage this data in a couple of ways. I could suggest that if you had a bottleneck in a pigment grinding operation, if you were space limited in a pigment grinding operation, there might be an economic value here and that you could grind more pigment in the same amount of time if you were to use multifunctional AAAs as compared to less functional, very hydrophilic, simple alkanolamines or ammonia type base. And then if you just take the grind, the fully mixed grind from the previous experiment, and you dilute it by 21%, and then take a single point viscosity measurement, you just see duplication of the effect that is noted on the graph between the hydrophilic, the very hydrophilic alkanolamines, the somewhat multifunctional alkanolamine, and maybe what you call a completely multifunctional alkanolamine. So now we'll move on to case study 3, the impact of the alkanolamine structure on emulsion stability. One significant off-diagonal effect of certain additives, like alkanolamines, is enhancement of colloid stability. There's a number of colloidal systems in latex paint. There's emulsions and pigment dispersions and other type of colloidal systems. And the use of structurally appropriate multifunctional alkanolamines can significantly enhance colloid stability in the overall paint. Today we've chosen to demonstrate that with some experiments that show improved resistance to cineresis. We've done some actual measurements of liquid interfacial tension, and we can show the implication of that for colloid stability. And we have a couple of demonstrations of reduced film stress during drying. So again, we'll just sort of start with a standard paint. We have a VAE type, VAE resin type paint, oxazolidine biocide, dispersants and surfactants from various producers, all sort of very standard stuff. A thickener from Ashland, we use DuPont TiO2 in this case. In any event, at one point we took this sort of standard paint that we were working with. We were doing a number of experiments with it, and we decided to do a side-by-side comparison of amines with different HLBs. The HLB is an acronym for the hydrophile-lipophile balance. It's a very standard measurement that's applied to surfactants. It can be calculated in different ways. There are normally precedented means for calculating the HLB. In the case of ethoxylated fatty alcohols, one takes the hydrophilic portion of the molecule, which would be the molecular weight of the ethylene oxide, and divides it by the total molecular weight of the molecule, and then multiplies that by 20. Now for other molecules, you can develop alternative calculations of the HLB. The only thing that's really important is that the calculation be applied consistently across that entire class of molecules. What we adopted was a calculation that's very similar to the one used for fatty alcohol ethoxylates. We take the alkoxylated portion of the alkanolamine and divide that molecular weight by the total molecular weight of the alkanolamine, and then divide by 20. The thing to bear in mind is that these alkanolamines do not imply surfactant-like behavior for these alkanolamines. Ammonia monoethanolamine would have an HLB of 20. Fatty amines would have HLBs of about 4. Functional alkanolamines have HLB in the 9 to 15 range. But certainly don't conflate those HLBs with the HLB values that you would calculate for a surfactant. We use these HLBs just so that we can put a number on the x-axis. We don't want to constantly have bar charts where we've identified the different alkanolamines as A, B, and C. There's less information in that type of a plot. If we can instead plot some numerical value that has relevance for the alkanolamines, we get much more coherent trends when we look at different things like pigment dispersion efficiency or something versus HLB. That's a much more scientifically valid plot than you just do a bar chart with a bunch of different alkanolamines and show various degrees of pigment dispersion enhancement. So in any event, when we take a look at this experiment, we took 3 paints and we wanted to look at syneresis control after 1 week, stirred, and then look at separation after 1 week. So we can see that this paint made up with ammonia separated completely, and that this paint made up with multifunctional alkanolamines, this is better than this if you look at it carefully, but still there's a significant amount of separation with this more hydrophilic alkanolamine. But that alkanolamines in the 9 to 12 range seem to be ideal for enhancing syneresis stability over an extended period of time. Lower HLB alkanolamines tend to be difficult to work with. When you get down to the lower HLB levels, you start to have more of an oil-soluble material that's not characteristically used in this application. So at one point in our work in this area, we got curious as to why this might be. What are some of the mechanisms behind colloid stability increases as a function of alkanolamine structure or alkanolamine HLB? And so we took a look at this concept. This cartoon represents the formation of an oil and water emulsion. You've got an oil phase and a water phase fully coalesced here on the left, and we mix that up with a high-speed stir, and then we have an emulsion, which is a continuous phase of dispersed oil drops, a continuous phase of water with a dispersed phase of small oil drops. So we have a 2-phase system which is mixed up into a colloidal oil and water emulsion. And just using some simple physical chemistry, we said, what's the difference in the energetics between the before and after situation? So we added up all the energies of the different interactions that are occurring before and after. And what you know is that most of these energies are the same. The free energy of the water and the oil, et cetera, are all just about the same before and after. The only term in this equation which is significantly different in the before and after case is the interfacial tension between the water phase and the oil phase multiplied by the increase in the interfacial area of those 2 phases. So this is the well-known term of importance in emulsion stability. Now, the interfacial area between the water and the oil phases is set by the size of the oil droplet. So that can't be changed. Well, it can be changed a little bit by the speed of the stirring, but that's not a variable that we can do much about. But as a formulator, you can ask yourself, how can I minimize the interfacial tension between the water and the oil phase? Because if you reduce that to the minimum level obtainable, you'll have the least driving force for coalescence, so you should therefore have the most stable emulsion. This is an examination of the thermodynamic driving force for emulsion for breaking of an emulsion and recoalescence of the two phases. This would be a lot different from some of the other mechanisms that are used to stabilize emulsions, which are more kinetic in nature. But in any event, for this particular development, the water-oil interfacial tension is the important parameter. Now, liquid-liquid interfacial tensions can be measured. This is different from the surface tension, the characteristic surface tension, which is the interfacial tension between air and a liquid phase of some sort. What we're now measuring is the interfacial tension between two liquid phases. And you can do this in a number of different ways. The tape method from the 19th century is a good way to do this. You can take a pipette with an orifice of known radius, and you can simply create drops of one phase in the other phase. Just create the drop very carefully and very slowly until it breaks off the tip of the pipette and let it fall into the other phase. You take the weight of those drops. So you do about 10 drops per experimental run, and then you statistically average over a number of experiments, but eventually you calculate a drop weight. So you could do this with, say, oil. You could take motor oil and pure water. Just take your motor oil in a pipette, just immerse the pipette slightly below the surface of the motor oil, the motor oil, yes, the more dense material has to be dropped into the less dense material. That's an experimental practicality. You have to have the more dense material fall into the less dense material in order for the experiment to work. But simply take your pipette with your more dense liquid, immerse it slightly below the surface of the other liquid, and then create drops very carefully. And then just do this on a top-loading balance and take the weight of the drops. If you take that drop weight and divide it by the radius of the orifice in your pipette, you've got the liquid-liquid interfacial tension. This was published by Tate, an English scientist in the 19th century. It's a good method. It's prone to quite a few errors. There's a lot of physical things that happen with ejection of the drop too rapidly from the orifice, but it's a great way to start. Just collect some sort of basic initial numbers for a liquid-liquid interfacial tension. There's other ways. Probably the most sophisticated method of doing this is to use drop shape analysis. There are instruments that are sold to do this on a routine basis. And then there's another method. You can use capillary contact angle, and that's the method that we opted to use because we had done some developments in that area. So what we opted to do was to use the capillary contact angle method. In this method, you simply take a capillary tube and fill it with the two phases you want to measure the interfacial tension difference between. You measure this capillary contact angle here. You take a digital photo and you expand it, just making sure that none of the dimensions in the photo have changed. And then you can just use a compass and a ruler to measure the angle directly using geometry. And there's a paper that describes the use of this method in detail. If you're interested, we can give you the reference to that. We validated this new method with comparisons to bubble pressure. One can take drop weight versus bubble pressure. Bubble pressure is a very commonly used method for measuring a liquid-air interfacial tension. And so we did a comparison of drop weight measurements versus bubble pressure because you can't use the drop weight of a liquid falling into air as a measurement of the interfacial tension between the liquid and air. The two phases don't have to be liquids. They can be liquid or gas, or any two phases which will work, where the one drop will fall into the other phase and can be weighed. So we had a pretty good correlation line between drop weight measurements and bubble pressure, and then we applied we did that same correlation with drop weight measurements versus the new contact angle method. Now, in the case of the contact angle method, we did see a few deviations from the line, but that's characteristic for measuring liquid-liquid interfacial tensions. There are a number of experimental subtleties, and to really do it carefully, you would use a full drop shape analysis. But we collected some initial data this way, and here are the plotted results. So the three organic liquids that we examined were soybean oil, methyl oleate, and dodecaine. And the aqueous phases that we looked at were alkanolamines dissolved in water. So we had 0.5% alkanolamines dissolved in water, we had 1% alkanolamines dissolved in water, and we had 5%. And we arrayed these alkanolamines from HLB20, less functional, very hydrophilic alkanolamines, all the way up to higher molecular weight, more structurally elaborate alkanolamines. The effect is certainly more noticeable as you go to higher concentrations. And at 5% alkanolamine in water, you see some pretty significant differences in liquid-liquid interfacial tensions as you go to these mid-range HLB, more multifunctional alkanolamines. And we think that this type of an effect is a good explanation for many of the colloid stabilizing benefits of certain alkanolamines. Pigment dispersant enhancement, emulsion stability enhancement, and other things. Now, one question that we get commonly about using higher molecular weight, more structurally complicated amines is that they are going to be more slowly evaporating. So isn't there an issue with leaving a water-soluble amine in a coating longer? Isn't that going to degrade the water resistance? So we did do some water resistance experiments where we compared mid-range HLB alkanolamines to higher HLB alkanolamines with higher vapor pressure. The expectation in a comparison like this would be that the lighter alkanolamine would evaporate more rapidly and therefore would render the film less water sensitive. But we saw in the first 24 hours the opposite effect. And one way to rationalize this is to take a look microscopically and to note that this film is less permeable, more coherent. And that could be a result of enhanced colloid stability, of enhanced emulsion stability, of a reduction in the interfacial tension between the different phases of this coating. So if it's less porous, you can lay a wet paper towel on the top of it and not get all this boiling and bubbling that's just a result of the water entering the film through cracks and other porous openings. So finally, I'd like to talk about a fourth case study that shows the utilization of this strategy to develop an optimal paint formula. And this is to use an even higher molecular weight alkanolamine as a partial coalescent. We have a basic experiment. Again, this is a very simple paint with a DuPont titanium slurry, propylene glycol antifreeze, standard defoamer, biocide, etc., Roman Haas, acrylic resin, a little bit of Texanol in some cases, surfactants, etc. The variable in this latter study was the combination of the amine and the Texanol. What we did is to regard the combination of the amine plus the Texanol to be one system. In other words, the total coalescent in the paint was regarded as the additive contribution of the Texanol and the alkanolamine. So over here on the right, we started with the initial formulation, which was about 3.2 pounds of the amine and about 9.6 pounds of Texanol. We then varied that system to incorporate progressively less Texanol and progressively more alkanolamine. And we wanted to look at the impact that change had on the performance of the paint. Now, given that we're focused on the coalescent, the thing that the performance parameter will measure, of course, is film formation, or minimum film temperature, or something like that. So we took a look at low temperature film formation. And what we saw in the case of the initial formula, which was a formula that was optimized for AMP and contained a little bit of alkanolamine and a lot of Texanol, we saw that the multifunctional alkanolamines had good low temperature film formation, that an ammonia-based comparative formulation did not. But then as we progressed to higher and higher levels of alkanolamine in the combined alkanolamine-Texanol component, we immediately observed that the more mid-range hydrophilic medium functional alkanolamines lost good film formation, whereas the Vantex T-based formula maintained good film formation all the way out to about 62% of the alkanolamine in the combined coalescent system. And this was consistent for treated and untreated paper. Typically do both types of paper. So now one way you might use this would be if your alkanolamine is low odor and zero VOC, which is the case for Vantex T. The only reason you would replace a coalescing solvent, which is generally a little bit less expensive than an alkanolamine, would be as if you could obtain other benefits. And in this case, you can obtain a lower odor, lower VOC formulation via this substitution. So now I will move on to talk about a couple of other things, a couple of the other benefits of off-diagonal effect optimization. In addition to saving money, you can reduce the odor of paints, you can produce lower VOC paint formulas, you can produce more ergonomically compatible, better HES, health, environment, and safety type formulas. Fairly obvious thing one can do is a comparative odor analysis. One can take bottles of the different amines that are under consideration and just smell them. Now, most people have difficulty dealing with olfactory fatigue and the other variables that are necessary in doing a really good comparative odor study. This work was done in the old days when the business that I'm discussing was part of Arkema. That business was sold to Taminco about 7 years ago. A group in Lac, France, who are trained for doing subjective odor analysis, developed some quantitative values for the relative odor of different amines, and they returned values like this. So monoethanolamine exhibits more global amine odor than does Advantex, which in turn exhibits far greater amine odor than Vantex T, which is a much higher molecular weight and more associative alkanolamine. So there's really nothing too miraculous about this. One can do the same thing just by opening the bottle and smelling it, but there are quite a few things that happen when you do comparative odor analysis. You have to be careful not to compare aqueous solutions to pure materials. If you have an 80% aqueous solution of one material and you have a neat sample of the other material, you should dilute the neat material to 80% before you do a comparative odor analysis, because the partial vapor pressure of the water can significantly influence the way your nose interprets the odor. And you have to be careful about the distance of your nose from the bottle and olfactory fatigue, etc. So it's generally better to use a group that's trained in this manner if you want to develop real consistent numbers, but certainly people do this all the time. They simply open the bottle and judge for themselves which one smells worse. But we can move beyond a simple odor comparison and talk about the greater goal of odorless and zero VOC as an ergonomic goal for the future. You're aware that in the US and in Western Europe, there is a move to develop zero VOC paints. And generally, a zero VOC paint should have zero odor, because if there is nothing in the vapor phase, then there should be zero odor. So I have a graph that shows vapor pressure temperature profiles for a number of amines. The amines are not identified, but this is the blue line is a very low molecular weight hydrophilic alkanolamine. The red line is Advantex. That's an intermediate multifunctional alkanolamine in terms of vapor pressure. And then the green line is Vantex T. Theoretically, nothing has absolutely zero vapor pressure at any given temperature. There's always some vapor pressure. So at some point, regulatory agencies will need to decide what's a regulatory zero VOC versus some theoretical zero VOC, which does not exist. But right now, it looks like that decision is being made. There's a number of methods being developed, GC methods, thermogravimetric analysis methods, oven evaporation methods, and that debate is ongoing. But generally, the situation will end up something like this. You're going to have very hydrophilic volatile amines, which will be 100% VOC. You'll have some materials like this red line, which unfortunately are going to be categorized as 100% VOC. They're far less volatile than let's say, the worst offenders in the category, but they're still going to be called 100% VOC. And then you'll have some molecules which will be categorized as zero VOC. And they should certainly pass chamber tests and exhibit no odor. And this is what we have with Vantex T. Now, that's a much higher molecular weight. It has poor neutralization efficiency. You'll generally have to use 2 to 3 times as much as you would ammonia or a more hydrophilic, lower molecular weight amine. But you do gain all the multifunctional benefits. So in some cases, you can replace other additives like the coalescing solvent, some of your pigment dispersant, some of your emulsifier, and end up with a cost-equivalent formulation that has zero odor and a very low level, at least a very low level of VOC. We're hoping that it's going to be categorized as a zero VOC, but that development is still ongoing. There's nothing which is officially a zero VOC or a VOC yet. And then finally, I'd like to comment on a few starting points for this type of off-diagonal effect optimization, because I would assume that a paint formulator engaging in this type of an activity, he or she would have a paint of interest. They have a certain slate of additives, a certain set of paint performance parameters that need to be met, and they're going to ask themselves, can I do better with one of these other additives, let's say one of these other alkanolamines, as opposed to the one that I'm using right now. So where do you start in a study like that? The easiest place to start, of course, is at a pound-for-pound replacement. So what I have here are 4 paints, again, just a real typical sort of a paint, a couple of novel additives, a biostable HEC thickener, and a dendrimer-type defoamer, but other than that, very standard BIT biocide, pigment dispersant, surfactants, TiO2, standard suppliers, etc. And a VAE resin, a little bit of Texanol and defoamer. And I forgot exactly which alkanolamine this was adjusted with to begin with. It was either the monoethanolamine or the AMP, but it wasn't the Vantex T or the Advantex. So you take that 2.5 pounds per 100 gallons that was used for whatever alkanolamine was in there before, and you substitute the same weight of the alternative alkanolamines in place of it. And so we've done that here, and we have 4 comparative paints to take a look at. The comparative performance of those 4 paints is very similar, other than the pH. The pH of the higher molecular weight, lower pKa alternative alkanolamines will obviously be lower than the pH of a paint made up with a lower molecular weight, more efficient neutralizing alkanolamine. But other than that, the performance of these paints is very similar. Water spotting and blister resistance and scrub resistance, low temperature film formation, etc., color change, all very good in all 4 cases. So if you were to come across a situation like this where you were looking into changing additives and you ran 4 side-by-side comparisons with a pound-for-pound replacement of new additives for the old additive, and you found 4 paints that performed identically, you're in a pretty good position to move on. I would suggest now that if you examine latter studies with some of your additives relative to the more complicated additive, the alkanolamine as we're speaking of today, you're going to be able to reduce some of those other additive levels, because you're going to find that your paint has suddenly become over-dispersed and over-coalesced. And in some cases, that over-coalescence or over-dispersancy may degrade the performance of the paint. So you may find that by reducing some other levels, the paint performance improves. But I think this case is far more typical. You're not really going to have anything jumping out at you showing you that the paint is over-dispersed, and you'll have to find that through a latter study. One notable improvement here, though, was that when we looked at the pH stability after heat age for the Vantex T, whereas it starts at a lower pH value, its pH stability on heat age is much better. And that makes sense. This is just one of the benefits of examining alternative structures for your additives. Alkanolamines like Vantex T have a pKa slightly below the set point pH for the paint, for typical paints. So as these paints develop acid upon heat age, ester hydrolysis, microbial activity, whatever acid-generating mechanism occurs, they move from a position above their buffer point into their buffer range. These other alkanolamines are caustic with very high pKa. Once you set their pH at, I'm going to say 9, which is below their pKa, once acid starts to be generated in those paints, they are already below their buffer range. So you get much greater changes in pH per milliequivalent of acid generated in a given system. So this was something that we observed as we ran a bunch of these comparative paint studies, and it's one example of a benefit that you can get by looking at alternative structures for the various additives that you're using in paint. So finally, in conclusion, I hope we've convinced you that multifunctional alkanolamines, multifunctional additives in general, provide better value in terms of overall performance per price for the additive. This could include things like enhanced pigment dispersion, a notable example for multifunctional alkanolamines. In some cases, the use of lower pH set points and or an open mind about where the paint parameters need to be is useful. In some cases, the replacement of coalescing solvent allows for nearly equal cost reformulation. Slower evaporating multifunctional alkanolamines not only result in lower odor, lower VOC formulas, but they can also lead to better drying, less stress in the coating during the drying process, which can result in film improvement benefits. And finally, just in general, multifunctional alkanolamines, multifunctional additives in general can function as supplementary colloid stabilizers across the gamut of colloid systems that exist in pain. So finally, I'd like to thank you for your attention, and I'm certainly willing to try to answer any questions that you